Hi, and welcome to this presentation on the introduction. So what we will cover in this presentation. So we're going to look at what fascia is, so the different types of fascia we have in the body, and also the cellular makeup of fascia within the body. In this presentation, we will discuss what it is based on some more of the current research. There are lots of thoughts and opinions on what fascia is, as I mentioned in the intro slide, and this was discussed in a lot of detail by Robert Schleib in some presentations this year at the in 2018 Fascia Symposium. So we're going to discuss the components of fascia within this presentation, but then we're going to cover the role of fascia and instrument-assisted massage in a later learning. So what is fascia? Fascia is a three-dimensional web that embodies cells, nerves, and it is the immediate environment of all of our trillion cells. So it embodies every part of our body. It's innervated by nerves and contains 100 million sensory receptors, and that was from a study by Grunwald in 2006. And one of the arguments that occurred, or discussions that occurred with Robert Schleib and some of the fascial anatomists, was that is it a sensory organ? And initially we thought that there was nearly 10 times as many sensory nerves within the fascia than there are in the muscles. And that was Robert Schleib and others, their initial view on fascia and the sensory receptors. But from a study by Grunwald in 2006, he discovered that there was nearly 100 million sensory receptors. And this was discussed at the Fascia Symposium this year. So it's a really sensory-rich part of the body and sensory-rich tissue, which makes us think in terms of the hands-on work and the therapy work, we're affecting the fascia through the nervous system, which we will cover later in later presentations. It's often divided into sections and subsections, so that's different parts of the body, and different sections have different names to it. So we'll discuss that later as well. And the terminology is often interchangeable, and the definition of fascia is completely interchangeable depending which therapist, which anatomist that you speak to. And there was discussion about this within the 2018 Fascia Symposium and then previous ones, and also at the Fascia Conference in the US as well. And what they discovered is they were all thinking the same thing on what fascia actually is, but the terminology they used was slightly different. So the terminology for different sections and subsections was slightly different. So we're going to cover what the majority thought in terms of the subsections and the different areas of fascia within this presentation. So it's often divided into four main sections. We have the superficial fascia, the deep fascia, the meningeal fascia, and the visceral fascia. So let's explore each one. So the superficial layer of fascia is the layer of fascia that's directly underneath the adipose tissue, so directly underneath the fatty tissue and the skin. It separates the skin from the muscles and allows that slide and glide to occur from the tissues. But it's also involved in functions such as thermoregulation, circulation, and for the lymphatic system to flow throughout the body. The next is the deep fascia. Now this is a real dense, fibrous layer of fascia. It's considered like a body stocking or a catsuit, and if you've seen some of those anatomy images of fascia and about that huge body stocking, that's what they're referring to. It encompasses each muscle and it separates but also connects everything together. It's also the layer that force transmission takes place within the fascial system. So it allows us to move and it transmits force from one part of the body to another part of the body. And it can really affect neighboring muscles or even completely different areas of the body. That's why sometimes you might feel a stretch in one area and then you'll feel that through into a completely different part of the body. And it's this layer of fascia that we think of when we're looking at maps such as the anatomy train's myofascial lines. The next is meningeal fascia. Now this one is the fascia that surrounds the nervous system and the brain. And then lastly, the visceral fascia, and that one surrounds the organs of the body. Now fascia is both elastic and plastic, so it's made up of fibers, but it also has a fluid property to it. So it's known as a colloid substance. If you think of like a rubber band and how it pings back to normal after it's been stretched out, but it also can deform over a long period of stretching over time. And we'll discuss that later on in the course. So fascia is made up of two different components. The first one is extracellular matrix, or ECM, which is made up of ground substance and fibers such as collagen and elastin, and then also cells. And cells is made up of mostly fibroblasts, other cells such as telocytes, and then nerves and vessels. The extracellular matrix. So this is a substance that's within the fascia. It's the colloid substance where it's both fluid and fibrous. And it's made up of the collagen, elastin, and that ground substance combined, which creates that colloid style substance. Ground substance. So ground substance is a fluid part of the extracellular matrix, and it's where the chemical exchanges take place. As Johan described in his book, it is the immediate environment of every cell in your body. It fills all the spaces between the fibers and the cells and contains around 15 litres of water. This fluid is interstitial fluid, and it's responsible for the transportation of nutrients and has roles in such as remodeling of tissue, inflammation, and also lymphedema. And it's also really vital to maintain healthy tissues and homeostasis within the cells. And the connection between the extracellular matrix, the ground substance, and the cells is a cell receptor called integrin, which permeates the cell from the extracellular matrix, which we'll discuss in a few slides' time. So elastin and reticulate. Now these are two of the fibers that you find within the extracellular matrix alongside collagen. So elastin does what it sounds like. It's the elastic fiber within fascia that it gives it that resiliency. And it's elastic so it can stretch quite far, up to 230% of its original length. So reticulum is formed by the type 3 collagen, and it's mostly part of the collagen that's formed within organs. It's not found in every type of fascia. Collagen. Collagen is the most abundant protein in the body, and there are at least 15 different types of collagen that have been recorded. However, the cum bono study suggests there are at least 25 different types of collagen, so the research is still inconclusive. Type 1 collagen is the most abundant in the body, around 90%, and it's found within the skin, the bone, tendons, ligaments, and within the fascia. But fascia itself can contain an array of different collagen types, according to the cum bono study, suggesting that it's not limited to types between 1 and 24. The shape of collagen is a triple helix shape, which gives it its tensile strength, and gram for gram it's been suggested that collagen is stronger than steel. So it's a really strong fibre within the body. And it's also thought to respond to Wolff's law. So Wolff's law is the bone's ability to adapt when regular loads are placed on it, becoming stronger. So mechanical stress, mechanical force over time increases the osteoblast activity, strengthening bones and increasing bone density. And it's been thought that collagen has a similar response like Wolff's law. And as you can see here, there are three different images of collagen. So the first images A and B. So A is a normal soleus muscle and B is a normal gastrocnemius muscle. So the collagen fibers within these tissues. And then it shows C just below, which is the collagen fibers of a soleus muscle that has been immobilized. So going back to the Wolff's law and how we think collagen may respond to Wolff's law, over time with immobilization, so lack of movement, collagen forms in a less linear pattern and more wiry pattern. Piezoelectricity and mechanotransduction. Piezoelectricity refers to the ability of certain materials to produce an electrical charge in response to mechanical stress. So a process where the tissues and cells respond to a new mechanical stress. So the example would be Wolff's law, so how the bones adapt to stress from a certain movement over time. And the example is the study by Taylor in 2009. And what they found was that the humerus bone of an advanced tennis player's racket arm was more dense than their non-racket arm. So what had happened is, to respond to mechanical stress, the osteoblasts had increased production, increasing bone density. So scientists think that the same can happen at a cellular level, which is known as mechanotransduction. So within the cellular level, mechanotransduction can occur. And going back to the cell receptor integrin that we mentioned earlier in the slides, which is the one that permeates between the extracellular matrix and the ground substance within the cell. And that cell receptor is the one that responds to mechanical stress and tension. So as it experiences tension through the extracellular matrix and through the ground substance, can then affect what happens within the cell. So they respond to that mechanical stress. And this mechanical stress can then impact the collagen synthesis via the fibroblasts. So the collagen synthesizes more from the fibroblast activity, responding to mechanical stress. And here is a little diagram just going through that and giving that example. So you can see the integrin, which is the A strand, and that permeates between the cells. So the cell is the blue area and the white area is extracellular matrix. And then those strands, that crisscross strands, those are the fibers of the collagen, the elastin and the reticulate. So what can happen is, as that tension increases within the extracellular matrix, it stimulates the integrin, which is responding to the mechanical stress, which then makes a change within the cell. And you can see this in a little bit more detail in the YouTube video, The Inner Life of the Cell, which is in your online learning to watch after this. Fibroblasts. These are the most abundant cells within fascia. And what they do is they produce and maintain the extracellular matrix, but they're really responsible for the synthesization and the remodeling of collagen depending on where the tension is. So going back to the integrin and the pull of the cell, those are responsible for creating and remodeling collagen depending on where tension is and mechanical stress is. So scientists used to think that the collagen formation from fibroblasts was more linear, but some research from Grinnell in 2007 and Jumbarteau in 2007 found that they form more of an organized 3D matrix, so it's a little bit more disorganized. Fibroblasts also have the ability to morph into myofibroblasts, which help with wound closure at the cellular level. So the myofibroblasts are part of the inflammatory response and wound healing. Fibroblasts are also responsible for the tissue homeostasis, going back to adapting through mechanical force and synthesizing collagen and remodeling collagen where tension is. They interact with the collagen fibrils, which then transmits force in a certain direction to maintain tension or balance. So they'll keep remodeling collagen to maintain tension or balance wherever that force needs to happen. What they do need is a stimulation to produce the collagen. And Grinnell in 2007 found that when there is low tension and low stimulation, collagen production reduces. And when there is high tension and more stimulation, collagen production increases. So going back to that image of the 3 different types of collagen from the gastric and the soleus, and then looking at the soleus tissue of an immobilized tissue, you can see there's low stimulation, so there's less collagen being produced than when muscles and tissues are more active. So what fibroblasts do is they synthesize collagen where there is more pull and then secrete collagenase, which is the enzyme that mops up collagen where there's less pull. And it's all based on vibration and information based on the mechanical stress and tension. And then lastly, another part of the cell makeup is the telocytes. And some research in 2006 by Cratio found that there is another cell within fascia known as a telocyte. And these telocytes, so these cells, are mechanosensitive cells, and they're vital for many physiological processes such as tissue repair and immune function. And these are also communicators and can share information and genetic material to other cells. But the research is still quite new on these telocytes, but it is a big focus in current research within fascia today. So this image is from Jumbarteau, and it's from the video Strolling Under the Skin, and there is a video in the online learning of that, a YouTube link of that video, and I recommend giving it a watch. So this just shows how one fascia is completely disorganized, so you can see here that disorganized web, but what it does do is it doesn't stretch or come away when there is that sliding guide. So from muscles and bones move away from each other, muscles and tissues move away from each other, then that fascia organization is still disorganized, but is still intact. It doesn't lose any connection. So in summary, fascia is abundant with sensory receptors which we can affect within massage. It's made up of extracellular matrix, collagen and other fibers within the extracellular matrix, and fibroblasts. And these fibroblasts synthesize the collagen where there is tension and mechanical force, so they move depending on the stress within the body and the tissues to maintain balance. So potentially fascia collagen responds to Wolff's law and changes depending on the mechanical stress that we endure on our bodies. And finally, here are some of the references based on what we've discussed in this first fascial learning. And as you can see there, just about 2/3 of the way down, halfway down, is the Giambato video. So I recommend giving that a watch. That is also in your online learning. I hope you enjoyed this anatomy, and we're going to head to the next video and the next presentation, which looks at fascia and the nervous system.